Hey everybody, welcome back to our series on Vertex Operator Algebras. Today, we kick off the back half of Chapter 2, which involves a custom, very idiosyncratic discussion of conformal field theory, which itself is the physicist's name for Vertex Operator Algebras. We're going to kick things off with a lightning review of, well, basically all of physics, framed of course as a discussion of what might be the most important result in the modern era, Noethers Theorem. Despite its origins over a century ago, Emmy Noether's celebrated theorem lives on as a foundational insight that relates symmetries of a physical system to its conservation laws. But first, of course, the preliminaries. Much of physics is represented as problems in the calculus of variations, which you can think of as an optimization problem over a certain space of continuous functions of space and time. To that end, we begin with a study of spacetime, which, for our present purposes, is the vector space R4, equipped with an inner product, or fundamental quadratic form with mixed signature, if you're from the 19th century, giving time-like directions the opposite sign from space-like ones. Indeed, there is a precise meaning to these terms like time-like and space-like, depending upon whether the sign of the inner product of a vector with itself is positive or negative, respectively. A time-like vector can connect to points in causal contact. A space-like vector connects points that are not. Note that a vanishing inner product here has a much broader meaning than what you might be accustomed to. They represent points in R3+1 that can in principle be connected by a beam of light. A bit of notation here. This funny inner product is often represented by a symmetric matrix, G, known as the metric. The metric more naturally belongs to the study of Riemannian geometry, although that machinery won't be necessary for our current considerations. In practice, the indices of the matrix and vector products are typically written explicitly and used for aids in calculation. Indeed, in physical context, such indices appear precisely twice, so following Albert Einstein, we drop the summation sign as the sum itself should be implicit whenever indices are repeated. Also, the metric itself is often implicit, as it is always the case that one index is presented raised and the other is lowered when summing. If you are details-oriented, you are welcome to take care and define the dual space using the metric explicitly, but for convenience, we'll use the semi-implicit summation conventions of the physicist for these matters. I should pause at this point to say that the summation over indices is often the first major hurdle for folks intentionally studying physics, particularly gravitational physics. For me, it was like a notational brick wall that I had to throw myself against again and again and again until I broke through. If you're interested in physics, it may well be worth practicing as much as you can in these lectures to familiarize yourself with how these conventions work. Do not despair. It does become intuitive with time and practice. You totally got this. For these lectures, we'll be primarily interested in the physics of fields, which are some mostly smooth, possibly with manageable singularities, constructions over spacetime, R3-1. Typically, we think of them as vector bundles, which is a nice perspective as it generalizes easily to other base spaces, be they curved or of a different dimension. Typical vector bundles for us will be the boring ones, real and complex line bundles, which we now explore. Let L be a function of these fibers or fields, phi. The action, S, is defined to be the integral of L over the base space, typically again R3+1. From this perspective, we can frame our variation problem by considering how S varies with phi. Our specific aim is to find sections of the bundle for which the action is stationary as we perturb away from them. Another way to frame this principle of stationary action is to think of S as something of a Morse function of phi, and physical solutions to be the critical points of the action. That is, those points where the derivative of S vanishes. Keeping with this interpretation, degenerate or non-Morse critical points of S amount to very interesting solutions of a physical theory, often describing novel concepts such as second-order phase transitions and related ideas known as critical phenomena. But back to generic critical points for now. We consider variations of the fields and their first derivatives. We could, in principle, consider higher variations, although in our current formalism this would be superfluous as the physics sits on non-degenerate critical points, meaning that the variations of the higher derivatives of the fields at this point would strictly depend upon those that we already have. Incidentally, this is also consistent with the symplectic structure latent in virtually all physical systems in the following sense. The dynamics of a physical degree of freedom is often modeled as a Hamiltonian vector field on some symplectic manifold, where the dual coordinates x and p are represented by position and momentum of a physical object, as is the case with our field phi. The symplectic form scaffolds the dynamics, and is the point of departure for defining commutators in quantum mechanics. Okay, having thrown basically an entire year's worth of physics at you in one go, we now return to the variation of the action S. Integrating by parts, we find two terms. The first being the equations of motion, which give the condition for which the action S is stationary under the field variation delta phi. The second term, the boundary or surface term, is typically evaluated at infinity and amounts to choosing suitable boundary conditions on phi and its derivatives. While this often is, and is framed to the student as a trivial, if technical matter, the choice of boundary conditions can be surprising and very non-trivial. Indeed, many of the Vertex Operator Algebras studied in practice effectively amount to the boundary theories of some gravitational system. And perhaps more curiously, in some cases, the study of the boundary alone is enough to determine the entire theory. More on that, perhaps, towards the end of this course. Having discussed the physical dynamics, we now turn to the main topic of today's discussion, Noethers Theorem. Noethers Theorem regards distinguished variations of the action, and to that end may involve variations of either the fields, or fibers of the theory, or the base itself. These distinguished variations are those that preserve the equations of motion, perhaps up to a total derivative or a boundary term. We call such subclass of variations symmetries of the theory, or, model under consideration. Emmy Noether's big insight was that the symmetries of the action correspond to the physical conservation laws of that system. Those conservation laws can be explicitly written as follows, including a potential boundary or total derivative term. So let's make this discussion concrete, and perhaps prescriptive, by considering a few examples. Our first example will be a complex line bundle over R31. Our function L here will be quadratic in both the derivative and the plane terms. Here the bar refers to the complex modulus, and we've abused the notation somewhat by implicitly hiding a factor of the metric g without explicit repetition of the index. Since the action S depends only on the complex modulus of these terms, there is a natural continuous symmetry given by a complex phase rotation, e to the I alpha. For infinitesimal alpha, this amounts to a variation I alpha phi, which, plugging into our previous expression and summing over both phi and phi bar degrees of freedom, we find the current density, J. With a slightly more nuanced treatment of the dynamics, this current can be interpreted as the electromagnetic current. For us, conserved here basically means the divergence vanishes. Symmetries of the fibers are certainly interesting, but symmetries of the base itself are too. Perhaps the most basic of these symmetries of R3+1 is the translation symmetry, say setting x to x plus a for some vector a. Pushing this transformation forward to phi, we find an induced variation as the directional derivative of phi along a. Following the same prescription given above, we find 4 conserved currents, represented as a rank 2 tensor T. Note that the variation of the function L itself also occurs, and maps to an extra boundary term here. This packaging of 4 conserved currents, one for each of the components of the translation symmetry, is referred to as the stress energy tensor, and it will play a crucial role in our study of conformal field theory. Note that T is symmetric by the structure of the function L, and divergence-free as a result of Noethers theorem. As a final demonstration of Emmy Noether's celebrated theorem, we'll look at scale transformations of the base spacetime. That is, the multiplication of vectors in R3+1 by some real number lambda. Now, scale invariance is typically not a feature of physical systems, as anyone who has climbed a mountain may tell you. Indeed, a 50K run takes considerably more time than a typical 5K sprint. But in the spirit of investigation, let's follow our nose and see where this goes. The variation in phi induced by scaling the coordinate x is the inner product of lambda x with the derivative of phi. Does lambda really parameterize the symmetry of the system? Plugging into the formula derived from Noethers theorem, we find the associated current J sub lambda, which equals the contraction of the stress-energy tensor with a coordinate x. By definition, this current is conserved if its divergence vanishes. Taking its divergence, and remembering that T itself is divergence-free, we find that the divergence of the current J sub lambda equals the trace of T. Thus, scaling is a symmetry of the theory if T is also traceless. For a simple line bundle over R3 plus 1, the answer is of course no. But, as you might check explicitly, R1 plus 1 is quite a different story. And so, as a quick review, today we explored 3 applications of Noethers theorem. The first involved a symmetry of the fiber. The second involved the symmetry of the base. The third looked at Noethers theorem from a converse perspective, and also involved the base, and we saw how a distinguished variation might become a symmetry of the theory, provided the current is conserved. That is, provided, in this case, the trace of the stress-energy tensor vanished. And that's our show. Next time, we'll dive deep into the waters of conformal invariance.